Earthquakes. These natural phenomena are a powerful reminder of the incredible forces at work beneath our feet. Imagine the ground suddenly shaking, sending buildings swaying and creating fissures in the earth. But what causes these dramatic events? Let's delve into the science behind earthquakes and explore the forces that shape our planet. Earthquakes are more than just tremors. They are a testament to the Earth's dynamic nature. By understanding the science behind earthquakes, we gain a deeper appreciation for the planet we call home. From the movement of tectonic plates to the release of seismic waves, each aspect of an earthquake reveals the intricate workings of our world. To understand earthquakes, we must first understand the Earth's structure. The Earth is composed of several layers: the inner core, outer core, mantle, and crust. The crust and the uppermost part of the mantle form a rigid layer known as the lithosphere. Picture the Earth's outer layer, called the lithosphere, as a giant puzzle made up of massive pieces called tectonic plates. These plates are like the pieces of a jigsaw puzzle, fitting together to cover the entire surface of the Earth. These plates are in constant motion, albeit extremely slow, moving a few centimeters each year. This movement is so gradual that we don't notice it in our daily lives, but over millions of years, it has shaped the continents and ocean basins. This movement is driven by the intense heat deep within the Earth's core. The heat causes convection currents in the semi-fluid asthenosphere beneath the lithosphere, which in turn causes the tectonic plates to move. The Earth's tectonic plates fit together like puzzle pieces, but their edges don't always slide smoothly past each other. The boundaries where these plates meet are called faults, and they are often sites of intense geological activity. Sometimes they get stuck due to friction. This friction prevents the plates from moving, causing stress to build up over time. Over time, pressure builds up at these points of contact. The longer the plates are stuck, the more pressure accumulates, creating a highly unstable situation. When the pressure becomes too great, the plates suddenly slip, releasing a tremendous amount of energy in the form of an earthquake. This sudden release of energy sends shockwaves through the Earth, causing the ground to shake and sometimes leading to significant destruction. The boundaries where tectonic plates meet are called fault lines. These fault lines are like cracks in the Earth's armor, prone to slippage and stress. They are the zones where most earthquakes occur. There are different types of fault lines, each associated with a specific type of plate movement. For instance, at a normal fault, plates move apart, creating space. At a reverse fault, plates collide, forcing one plate over the other. And at a strike-slip fault, plates slide horizontally past each other. Each of these movements generates distinct seismic activity, contributing to the diverse nature of earthquakes. Imagine two tectonic plates pushing against each other, stuck at a fault line. These massive slabs of Earth's crust are in constant motion, driven by forces deep within the planet. When they collide or slide past one another, they can become locked due to friction, unable to move. The pressure builds up over time, like air in an inflating balloon. This pressure is the result of the immense forces at work beneath the Earth's surface, causing stress to accumulate at the fault line. The longer the plates remain stuck, the greater the pressure becomes. Eventually, the pressure exceeds the strength of the rocks, and they break. This breaking point is a critical moment as the stored energy is suddenly released. The rocks snap and shift, causing a rupture that sends shock waves through the surrounding area. This sudden rupture releases a burst of energy, creating vibrations that travel through the Earth's crust and cause the ground to shake. An earthquake is born. These vibrations, known as seismic waves, radiate outward from the point of rupture, shaking everything in their path. The point within the Earth where the rock breaks and the earthquake originates is called the hypocenter or focus. This is the underground origin of the earthquake, where the initial break occurs and the seismic energy is first released. The point on the Earth's surface directly above the hypocenter is called the epicenter. It is the location where the effects of the earthquake are usually felt most strongly, as it is closest to the source of the seismic waves. This is where the earthquake is felt most strongly. The intensity of the shaking can cause significant damage to buildings, infrastructure, and can be a terrifying experience for those in the vicinity. The depth of the hypocenter influences the earthquake's intensity and the extent of its impact. Shallow earthquakes tend to cause more damage at the surface, while deeper ones may be felt over a wider area but with less intensity. Section 5. Seismic waves, the ripple effect. The energy released during an earthquake travels in the form of seismic waves. These waves radiate outward from the hypocenter, much like ripples spreading from a stone dropped in a pond. There are different types of seismic waves, each with its own characteristics and effects. Primary waves, or P waves, are the fastest and travel through both solids and liquids, compressing and expanding the material they pass through. Secondary waves, or S waves, are slower and can only travel through solids, shaking the ground back and forth. Surface waves travel along the Earth's surface and are responsible for the most damage during an earthquake. Section 6. Measuring the quake, the Richter scale. Scientists use a tool called the Richter scale to measure the magnitude of an earthquake. This scale is crucial for understanding the power and potential impact of seismic events. By analyzing the data collected from seismographs, scientists can determine the strength of an earthquake and predict possible aftershocks. The Richter scale has been instrumental in advancing our knowledge of earthquakes and improving safety measures. This scale, developed by Charles F. Richter in 1935, assigns a number to quantify the amount of energy released by an earthquake. Charles F. Richter, a seismologist, created this logarithmic scale to provide a consistent method for comparing the sizes of earthquakes. His work revolutionized the field of seismology and provided a standardized way to communicate the severity of earthquakes to the public and scientific community. Each whole number increase on the Richter scale represents a tenfold increase in amplitude and about 31.6 times more energy release. This means that even a small increase in magnitude can signify a significantly more powerful earthquake. For instance, an earthquake that measures 7 on the Richter scale is not just slightly stronger than one that measures 6, it is exponentially more powerful. For example, an earthquake with a magnitude of 6.0 releases about 31.6 times more energy than one with a magnitude of 5.0. This exponential increase in energy release explains why higher magnitude earthquakes can cause much more extensive damage and are far more dangerous. Earthquakes with magnitudes less than 2.5 are usually not felt by people but can be detected by seismographs. These minor tremors, often referred to as micro-earthquakes, occur frequently around the world. While they don't cause damage, they provide valuable data for scientists studying the Earth's crust and the behavior of seismic waves. Earthquakes with magnitudes of 8.0 or higher are considered major earthquakes and can cause catastrophic damage. These powerful quakes can lead to widespread destruction, loss of life, and significant changes to the landscape. Understanding the magnitude and potential impact of these earthquakes is essential for disaster preparedness and response efforts. Section 7. History's Tremors, Remembering Earth's Power. Throughout history, earthquakes have left their mark on our planet, shaping landscapes and reminding us of nature's awesome power. The 1906 San Francisco earthquake, with a magnitude of 7.8, caused widespread destruction, while the 2011 Tohoku earthquake in Japan, with a magnitude of 9.0, triggered a devastating tsunami. These events serve as stark reminders of the destructive force of earthquakes. By studying past earthquakes, scientists can better understand earthquake behavior, assess risk, and develop strategies to mitigate future impacts. Section 8. Predicting the unpredictable, earthquake forecasting. While we can't prevent earthquakes, scientists are constantly working to improve our ability to forecast these events. By monitoring fault lines, analyzing historical data, and studying precursory phenomena like foreshocks and ground deformation, researchers aim to provide early warnings that can save lives. However, earthquake prediction remains a complex challenge. Despite advances in technology and understanding, accurately predicting the time, location, and magnitude of earthquakes remains elusive. Continued research and technological innovation are crucial for improving our ability to anticipate and prepare for these powerful events. Section 9. Conclusion. Respecting Earth's fury, preparing for the future. Earthquakes, with their awe-inspiring power, remind us of the dynamic forces shaping our planet. From the movement of tectonic plates to the release of seismic waves, these events provide a glimpse into the Earth's inner workings. While we cannot control these natural phenomena, understanding the science behind them is crucial for mitigating their impact. By studying earthquakes, developing early warning systems, and implementing earthquake-resistant building practices, we can strive to coexist with the Earth's dynamism. Respecting the Earth's fury and preparing for the future is paramount to ensuring the safety and well-being of humanity in the face of these powerful events.